Morning, everybody, or good night, or whenever you're watching this video. These are the notes for 16.1 in the physics book. I'm on page 558, and I'm kind of following along as I'm doing this. So I'm going to do it one section at a time. I know that you guys are busy. I know that there's a lot going on, but I really want to keep going with you so you can get to where you want to go and get to college and start life over soon, I hope. All right, so chapter 16 builds on chapter 15. This whole chapter is basically about potential, electric potential, which is really close to potential energy, but kind of different, okay? And then at the end of the chapter, they talk about something called capacitance, which we will talk about soon. All right, so they're taking you back through a review of potential energy, okay? If you remember gravitational potential energy, let me see if I can write. I did a video this morning and I was like killing everything here. PE MGH, okay? If you looked at the previous assignment, there's a worksheet that compares, takes you through potential energy problems, and then when you flip it over, the back is all about electrical potential, okay? So if you remember, we started talking about potential energy and how, like in a roller coaster problem, the motor does work, okay, that moves the roller coaster to the top of the hill. And then at the top of the hill, the roller coaster has potential energy. So this is sort of the same idea. Okay, let me hit the button here to move it up. Okay, so and just like gravitational potential energy, you can use electric force to figure that out. Okay, so electric potential energy, okay, is a thing because electric force is a conservative force. Okay, so we can kind of, there's a lot of parallels between like the force of gravity and electric force because the patterns are the same, although the amount is a lot different. Okay, so if you notice down here, this is the key part. Oh, I gotta hit the button. It's just like I'm at school, right? So the work done by a conservative force, either like, a normal force or an electric force, is equal to the negative change in the potential energy. Okay, so again, if we go back to my roller coaster problem, the work done to get to the top of the hill, right? So the potential energy here is equal, oh my God, that's so bad, is equal to the work and in this case, it's the negative work done to get to the top of the hill. Okay, so here we go again. Next slide. Okay, so the easiest way to explain this and to show you is to use a electric field between two plates, which is actually called a capacitor. Okay, so we have a positive plate here that's an area of high potential energy, meaning I have to do work to move a positive charge in that direction. And then on this side, I have a negative parallel plate, an area of lower potential energy. Okay, so if I take a charge right here, a positive test charge Q, and I stick it here, okay, it will move a distance of x. Notice this is a displacement, it is a vector, okay? As the charge moves, work is being done on it, okay? And you can see, here's the equation. Work done between A and B is equal to the force in the direction of x times the displacement x. Or, because we're using charge here, it is the charge times the field times the change in displacement, okay? So then if you notice here, all they did here was say change in potential energy is the opposite of work. So they flip this sign right here, okay? This equation only works in a uniform electric field, okay? When a charge actually goes along an axis. So if you're thinking like of a Van de Graaff generator, it's not along an axis, okay? It is a circular motion, and I keep doing that, and I need to stop. I wish it would realize what I wanted to do before I actually did it. All right, so I have to hit the little pointer button and move the slide. Let's try that again. There we go. All right, so if you notice, the SI unit of energy is joules, okay, and it stays that way. So potential difference. So the electric potential difference, or chain, or delta V, V is voltage, okay? So if you're a technician, like an electrician, and you're trained vocationally in electricity, you're using terms like voltage, okay? You're never probably going to use the term electrical potential, okay? If you're an engineer, you never use the term voltage because you're thinking more along the conceptual idea of electric potential, okay? So when you're out talking with someone in the world, you can kind of tell by how much they understand the concept of electrical potential by if they're using the term potential or if they're using the term voltage, if that makes any sense, okay? There's nothing wrong with being an electrician and using voltage, but it's a technician kind of thing where I'm attaching wires to a circuit to make energy flow, okay? Or I'm fixing a car battery, where if you're using the term electric potential, you're really doing concepts, okay? So electric potential difference, which is change in voltage, okay, change in V, between 2 points is defined as the change in potential energy, the final minus the potential of a charge moved, okay? So, keep doing that. Really annoying. All right, so if I want to know the change in potential between 2 points, okay, I need to do the change in potential energy divided by the charge. Okay, the potential difference is not the same as potential energy, however, they are related. Okay, all right. Another way to relate the energy is the potential difference. So the change in potential energy is Q delta V. Okay, electric potential energy and potential difference are both scalars, so that makes them very easy. And I promise vectors were going away, and guess what? They're gone. Okay. The units of potential difference are volts. Let me try to write this down here. Volt. Again, if you notice, we're in electricity, which means everything's in a capital letter, and that would be a joule. Oh gosh, this is a mess. Per coulomb. Oh God. Okay, it seems like when I swirl my pen, it goes away. I don't know, maybe it was just trying to figure out what I was doing. I don't know, there we go. Okay, so there is a special case like we were just doing, okay, between two parallel plates or in a uniform electric field, okay, where a change in voltage is equal to the opposite of the electric field in the x direction times the displacement x. Okay, this would also work for y as long as your field and your displacement are in the same direction, okay? And it gives you more information. So this would be newtons per coulomb or volts per meter. They're equivalent units, okay? All right, so then we're scrolling down here. This, again, is on that worksheet that I left, and I will give you the answers probably in this post, actually. So electric potential is the characteristic of a field only, okay? So it's how much work a field can actually do, okay? It is independent of whatever test charge you place in that field. It's just the ability of that electric field to do work, okay? It's a characteristic of a charged field system, okay? And we just did that. So it's a lot like gravity and things with mass, as you saw on that worksheet, okay? So if I take a positive charge, right, and I release it, it will automatically move from an area of high potential to low potential. So if you go back, way back here to the beginning slide, okay, if I drop this charge right here, it's trying to get away from this positive plate and get closer to this negative plate. That makes complete sense. And in the process, work is being done on it, okay? All right, back down here, almost through. All right, so if I had a negative charge, however, and I was moving it in the same field, I would have to do work to move it towards the negative plate. And that makes sense with the law of charges, okay? So the problems I will post for 16.1 are number 1, number 2, number 3, and number 6. They are all on page 593. Let me see if I can write this down without losing my mind. Page, oh my God, I have no idea what I just did. All right, I will post it. Here we go. Page 593. That's a 5, and a 3. Numbers, I don't know what it's doing. 1 through 3. That's a 3. No idea. And number 6. Okay, so work through those. Let me know which ones I need to do for you. And if you need any answers, okay? Good luck. I miss you guys a lot. I think about you a lot, and I'm kind of interested to see how this whole thing will work out. If I can do anything, please message me. I will try to do whatever I can for you, okay?